Hey everyone, welcome back, and today let's solve Leetcode problem 2523 titled Closest Prime Numbers in Range. So we're given two positive integers left and right, and we want to find two integers num1 and num2 such that they're both greater than left and less than right. And both num1 and num2 have to be prime numbers, meaning they're not divisible by 2, and the difference between the two numbers that we choose has to be the minimized among all the other pairs that are within that range that satisfy the above conditions of both being prime. And we want, of course, to minimize the difference between those two. And we want to return the positive integer array answer with basically both of those integers in that range, num1 and num2. Now, if there are multiple pairs satisfying these conditions, we want to return the one with the smallest num1 value, kind of prioritizing the smaller numbers. And if no such numbers exist in that range from left and right, we want to return -1 as our output. So in example 1, we have left to be 10 and right to be 19. The reason why we have an output of 11, 13, because 13 minus 11 is minimized of a difference of 2, and both 11 and 13 are prime, and both greater than 10 and less than 19, and yeah. Right, the closest gap between any pair would be 2, right? Technically, if we want to address all of the prime numbers and the range from 10 to 19, that would be 10, 11, 13, 17, and 19, right? It would be 10 to 19 inclusive, by the way, and between all of these prime numbers in the range, the closest gap, or the minimum difference between any two adjacent values, is of course 11 and 13, right? That's going to be 2, and so that's going to be basically our output. But another thing to note is that 17 and 19 also have a difference of 2. So why is 11, 13 the only input? Well, it also tells us that we want to return the 1 with the smallest num1 value if some pairs have equal differences. In this case, 11 is smaller than 17, and so we return the first pair of 11, 13. In example 2, we have our left to be right and left to be 4 and right to be 6. And in this case, there really only are, there really actually isn't, or rather, there really only is one prime number in the range from left to right. That would be the middle number 5. And so we can't actually satisfy the conditions above. 4 is even, 6 is even, 5 is the only possibility. Our num1 and num2 can't be equal, and so there's going to be an output of -1, right? We cannot satisfy the problem's conditions. And so for the constraints here, we're given that left is always going to be less than right, and they're both always going to be less than 10 to the 6th power, which leads us to some important observations to really make in this problem to solve it efficiently. Well, what is the main observation that really we can make, right? That is that checking whether a number is prime really can be slow if we do it individually for every single number in the range from left to right. And so to actually optimize that, instead of simulating checking for every number if it's prime or not in the range from left to right, every single number, instead we can use something called the sieve of Eratosthenes. I think that's how you pronounce it. I'm going to type it out as well. I don't exactly know how to pronounce it. It's going to be called the sieve of I think it's Eratosthenes. I don't really remember from the top of my head. And really, on a high-level rundown, what this really is, basically it's an efficient algorithm to actually pre-compute the primes up until a given number or input. And on a high-level rundown, the way our solution is going to work, effectively we're going to use this sieve of Eratosthenes to actually find or pre-compute all the prime numbers up until our right input, right? Because we're going to go all the way up until right, starting from left. And we have to only care about or extract the prime numbers within that given range from left to right, and basically just find the closest pair or the minimum difference by iterating through the list of primes and tracking that minimized difference. So let's go ahead and get into the code here. So what I'm first going to do is actually initialize something called the prime list. It's going to be a Boolean array, and it's actually going to be 2D. And so the way that's going to work, basically it's going to be true, and it's going to have dimensions of right plus 1. So rather, it's not 2D, sorry about that. What I really meant there, it's not like, what I really meant is that it's going to be initialized to all trues and have dimensions or a length of right plus 1. Now, what is the entire goal of this is prime list? Basically, it's going to have size right plus 1. All the values are set to true. It's going to help us track whether a number is prime. And initially, we're just setting all the values to be true, indicating that they are actually prime, but we'll change them if they are not prime numbers, right? Now, first, let's actually kind of get our base cases out of the way, right? Is prime at 0? That's our initial base case. And that's also equal to is prime at 1. That's the second value or second base case. They both have to immediately be initialized to false. This is what we build off of for future values. We know for a fact 0 and 1 are not prime numbers, and so we set their prime kind of Boolean value in the is prime list to be false because they're not prime numbers, right? So we're explicitly setting their values to false in the prime list because these are kind of like our initial values that we kind of start our is prime hash map is prime list with, right? That's kind of like our base case, right? Once we actually get 0 and 1 to be the non-prime numbers, or rather, yeah, the non-prime numbers, now let's actually implement the sieve of Eratosthenes, right? So the way this is going to work, it's going to basically have nested loops here for only the values that are actually prime, right? So basically for num, or every single value in the range from, we'll start from 2 because we already covered 0 and 1 as our base cases, and we're going to go up until the integer of right to the power of 0.5, basically just kind of like the square root, and we're going to add 1 to that to account for that 1 offset in for loops for second parameters, right? So for every single value in this range, if the current value is prime, so if is prime at the current value num, we know that we can actually iterate through all the multiple values in the range from the square of num up until right plus 1, right? So the way this is going to work, basically for multiple, and I'll explain how the syntax works in Python in a bit, in the range of num times num, or num squared, doesn't really matter how you interpret that. We're going to go to right plus 1, and we're going to increment by num each time, right? Now, what are we really doing in this case? In fact, let me just finish this up. We're going to set is prime at every value or multiple value in this range to immediately be equal to false. Now, what the entire purpose of this, or these 4 lines of code here, are doing, basically we're iterating from 2 to the square root of right? That's exactly what right times, or rather to the power of 0.5 is. And if any value num in that range is prime, we have to mark all of its multiples as non-prime. And we're going to start with its multiples from num times num. And that's going to very efficiently eliminate all of the non-prime numbers in that range for any prime numbers, right? Once we actually do that, now we have to actually extract the primes in the range. This is kind of like the second kind of thing here, or section here of this algorithm, right? So once we to actually extract all the primes in that corresponding range from left to right, we'll get the primes array, and I'm going to use something called list comprehension here in Python. It's going to be every single value or integer num for num in the range, or rather num, all the nums for every single number in the range from left up until left plus right. And to avoid for that, and to account for that offset in Python, I'm going to do plus 1 for for loops here, and we're going to do this. We're going to do this if it is prime. Basically, if it's prime at that number, we're going to actually get num as a prime in the range, or rather for all the numbers in the range from left to left plus right, right? Basically from left to right, right? Because we want to start with left and go up until right. So basically, again, using this list comprehension here in Python, the way we actually initialize lists in one line of code here in Python, we're actually collecting or kind of storing all the prime numbers in the range from left to right by checking is prime list, if it's actually prime at the corresponding value number, right? Now we have to actually find the closest pair. This is the main kind of section here. So the way we're going to do that is, first of all, quick conditional here. If the length of primes is less than 2, obviously we have an invalid input. We can't do anything. We have to immediately return -1 because we need at least 2 unique values to even have an output. We can't reuse any values, right? Because if there's no prime numbers or just one prime in the range, there is no pair, right? And we want to check for pairs and minimize the difference between them, right? Now, if there is pairs and we haven't entered this conditional yet, if we haven't returned anything yet, now let's actually find the closest pair of primes. So I'm going to initialize my minimum diff to simply be the float of infinity. That's what we're trying to minimize. So we'll get smaller and smaller from here, starting off as a very large value. And then I'm going to get my closest pair. This is effectively what I'm going to be returning. I'm going to initialize it to a -1, -1, but I will, of course, change it when I find a pair with a smaller and smaller value in each iteration that I iterate over the primes for, right? Basically, again, min diff is going to be infinity. It's going to be keeping track of the minimum difference, and the closest pair is going to be the closest pair output. It's going to actually keep track of the num1 and num2 output values. And now let's actually iterate over the prime list to actually find the closest pair and minimize that difference, right? So the way we're going to do that is basically for I in the range of the length of primes -1. And the reason why we do length of primes -1 is because we actually want pairs. So if we're at index at I, we also want index at I plus 1 to make sure that we don't go out of bounds, and we have at least 2 elements in every single conditional to check if that pair is a prime and minimized. In fact, we're actually guaranteed that all of these are primes because we are actually iterating over the primes list, right? So we're basically iterating over all the lists of primes and only primes in that corresponding range from left to right. So find the range of length of the primes -1 for all the pairs, we'll get the current difference to be primes at I plus 1 minus primes at I. And something very important to note is that we never want a value being subtracted by a much smaller or a much different value or much smaller value, right? Like we wouldn't want to subtract 19 by 11, or rather we want to subtract 13 by 11. Why is that? Well, because we know that adjacent values are always going to have the smallest values, right? Because the bigger the number gets, the bigger the difference gets, and we want to minimize the difference. And so we're going to go 11, 13, we're going to go 13, 17, and we're going 17, 19. 11, 17, 11, 19, 13, 19, they don't matter because that's just maximizing the difference, which we don't want to do. In fact, we want to do the opposite. And so we're only going to care about adjacent values because that's when we have the minimum difference between all the pairs, right? So once we actually get the current difference, if the current difference is smaller than the current minimum difference, than what we've seen so far, so min diff, I think is what I call it, well then we want to update our return value. So we'll get min diff, and now update it to be this new difference that we currently saw as the smallest difference so far, and update the closest pair, our output value, or our num1 and num2 values, to now be primes at I, and you guessed it, primes at I plus 1. The current element and the current element plus 1, or the next element after it directly, if it does actually minimize the difference after so far, right? Effectively, again, on a high-level rundown, we're looping through the list of primes in the range and computing the difference at each iteration between the consecutive primes to minimize the difference, and if we find a smaller difference between the current pair of values, we'll update the minimum difference and the closest pair accordingly for our output. And effectively, once we iterate over all the pairs and get the smallest difference or the minimized difference, we simply want to return our closest pair, or that list of length 2, with our num1 and num2 values. So unless I made any syntax error here, there should be accepted and there should be a valid solution. Let's go ahead and see what I did wrong here real quick. Left. Okay, I don't know why I have left plus right plus 1. Sorry about that, guys. Now there should be an accepted solution. Now this should work. Sorry about that. Let's go ahead and double check that. Okay. Once again, me with some very simple errors here. I'm going to quickly zoom out and try to troubleshoot. Feel free to just fast forward this part, guys. This is just me kind of being a little wonky with my solution. Again, feel free to just fast forward this part, guys. So we're saying that's false to the integer. Do have the integer if it's prime. Num times num. Right plus 1. Num, it's all fine. To be false. Num for num in the range from left to right plus 1 if is prime at num. Yes. Diff 30. Okay, so let's go ahead and see what's the error here. Sorry about that, guys. Again, feel free to just fast forward this portion. If diff is less than minimum diff, we'll get minimum diff to be the diff, and closest pairs to be primes at I and I plus 1. Okay, so I don't exactly know why this is giving me an error, to be completely honest with you guys. This seems to be completely correct in terms of code here. So feel free to just fast forward this part again. And yeah, I will tell you guys, I will also link in the video when I actually get the error. It's probably a very simple error. Just going to double check what actually is wrong here. So the length of primes is less than 2. We do want to return negative 2. Seems completely correct. Don't think there's anything wrong with that portion as such. Is prime is equal to true times right plus 1. Is prime at 0. For num in the range from 2. Right. If is prime. For multiple in the range num times num. Right plus 1 to num is prime at multiple equals false. And then we actually have to initialize primes. Seems completely correct, at least up until here. Left plus 1. If is prime at num. Nothing wrong with that either. Closest pair is equal to negative 1. Find the range of the length of primes minus 1. We'll get difference to be primes at I plus 1 minus primes at I. If the difference is less than the minimum difference, we'll update the minimum difference and get the closest pair to then be primes at I and primes at I plus 1 and return the closest pair. Okay, so I'm not exactly sure why this is getting a wrong answer. I will actually submit the code that I worked on just a couple minutes ago before this video in the description. Let's go ahead and get into why the solution works as a whole before we make this solution or video run too long, right? Effectively, on a high level rundown, what are we really doing here? Basically, we're iterating through all the values in the range from left to right and checking all the values that are prime and storing it in our prime array. Once we actually get those primes array, first, if we don't even have two elements, we don't have a valid pair, we immediately return -1 as an invalid output. If that's not the case, though, we iterate through all the primes in the range, we get all the differences between the consecutive primes and minimize the differences between all those pairs and effectively return the closest pair, the closest minimum difference pair. So for the runtime complexity here, for this solution, this is actually going to have a big O overall, or rather overall time complexity of big O of n times the log of n, right? We have a lot of logarithmic, it is a logarithmic time complexity, right? Because the actual sieve of arithmesis operation, that's going to be big O of n times the log of n is going to be equal to our right value. And to actually extract the primes and find the closest pair, those are both going to be linear big O of n times, and the overall complexity would hence be big O of n times the log of n. And that's going to be very efficient. And for the memory or space complexity, since we are actually storing this Boolean prime list, it is actually going to be big O of n, a linear time solution for the memory or space complexity. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.